Okay, guys, so stoichiometry, couple things to get us started is just in general, almost everything that we're going to be using in life is made through a chemical process, and those processes are made by companies. And so, why is stoichiometry important? It's important because when these companies make their products, they have to use the right amount of chemicals. They don't need to waste money on chemicals they don't use or need. And so that's one reason why stoichiometry is important. Um, Chemical equations are simply recipes. And so, for example, if I've got H2 plus O2 making water, and I balance that equation, then my recipe calls for 2 parts um, hydrogen to 1 part oxygen, and then we're going to produce 2 parts of the water. And so just keep in mind that equations are simply recipes for making whatever we're going to make. And then lastly, stoichiometry is the calculation of these chemical quantities. And so we are calculating the quantities of chemical reactions, and that is what stoichiometry is. Now, those quantities can be expressed in grams or liters. Those would be very common. Some units that we haven't learned about yet that we will, such as molarity, would be another example. So, some basics there. All right, stoichiometry with an everyday equation. So here's a recipe to make pancakes off of a Bisquick box. You need 2 cups of mix, 2 eggs, a quarter cup of oil, and a cup of milk, and you're going to get 8 pancakes out of there. 8 pancakes. So let's say you have family over, and you need to have 24 pancakes instead of 8. So the recipe tells us, since we're tripling this times 3, we would need to triple that. So we would need 6 cups of mix. We would triple that. We would have 6 eggs, and so forth and so on. And so that's effectively stoichiometry. It's calculating these quantities. How much do I need to make this is my calculation. And that's what stoichiometry does. And so here's a chemical equation. So 2 hydrogens plus 1 oxygen makes 2 waters. And so if you want to describe that in the terms of number of particles, then it's exactly that. It's 2 molecules of hydrogen will combine with 1 molecule of oxygen, and we're going to produce 2 molecules of water. Well, the important thing to go with this, or to understand with this, is that we are now going to interpret these numbers, these coefficients, as moles, because that's what we can measure out and weigh. And so we will, from here on, interpret that equation as, as 2 moles of hydrogen plus 1 mole of oxygen, and that's going to make 2 moles of water. And then we can convert our moles to mass or liters or whatever we need to work those problems out. So that's going to be our new interpretation of these numbers, that these coefficients represent the number of moles. They are the mole ratio, 2 moles to 1 mole. 1 mole here to 2 moles over here. All right, so we're going to skip that. Actually, we're going to right into the calculations. So the important thing on the calculations of stoichiometry is first you have to begin with a balanced equation. And so we just finished our equation chapter, and so you should know how to balance equations and finish out equations. And so we're going to produce ammonia from nitrogen and hydrogen reacting together, and so that gives us this equation, and this balances it. So the 3 basic steps that you're going to do in stoichiometry is, number 1, you are going to convert your given to moles. If it's not in moles, convert it to moles. If it is in moles, then skip step 1. Number 2, you will use the mole ratio between given and desired, if you will. And so, for example, in this particular question, we have been asked for how many moles of ammonia, NH3. And so if we're talking about ammonia, that's our desired, but we've been given 0.6 moles of nitrogen. And so our given is nitrogen and our desired is ammonia. And so our ratio between nitrogen, which is right here, and ammonia right there, our mole ratio is 1 to 2. All right, and then step 3, you will simply do another mole calculation conversion, convert the desired to the units that you've been asked to find, units needed. And so in this case, we've been asked to find how many moles. Well, this is easy. Moles is just, we're going to skip step 1, we're going to skip step 3. We're just using step 2. And so let's work this one out. And so if we have 0.60 moles of nitrogen, and we want to know how many moles of ammonia, then we will simply use the mole ratio between nitrogen and ammonia. And we're going to put the nitrogen, remember these are moles, this many moles and this many moles. And so we'll put the moles of nitrogen on bottom. And we'll put the moles of ammonia on top. And the ratio here is 2 to 1. So if you do 0.6 times 2, then you get 1.2 moles of ammonia, NH3. Okay, this is NH3, by the way, just make sure you understand. NH3 is ammonia, not to be confused with ammonium, which is NH4, one positive. Ammonium is the ion of ammonia. They are not the same thing, though. Okay, another example. How many grams of hydrogen are needed to react with 23.2 grams of nitrogen? So in this problem, we are beginning with what we've been given, which is 23.2 grams of nitrogen. We've been given grams of nitrogen here. We're going to convert that up to the mole, and then we're going to use our ratio to convert over to hydrogen, and then we're going to convert the moles of hydrogen back down to grams. And so those are going to be our processes. So we're going to convert this to mole. We'll use the molar mass of N2, which is 28.014. And what's 1 mole of nitrogen? And then we're going to use the mole ratio. For every 1 nitrogen, we'll need 3 hydrogens. So 1 mole of nitrogen to 3 moles of hydrogen. And we've been asked to convert our hydrogen into the unit of grams. How many grams of hydrogen? So we'll do that step using the molar mass of hydrogen. 1 mole of hydrogen is 2.0158 grams. So 2 hydrogens, 2.0158. So when you run this through your calculator, you actually come out with 5.0 grams of hydrogen. So you would need 5.0 grams of hydrogen to react with 23.2 grams of nitrogen. Again, making sure as you look at these problems that you'll cancel out grams of nitrogen, moles of nitrogen, moles of nitrogen, moles of hydrogen, moles of hydrogen. Everything cancels out top to bottom, not the numbers, but the units. So you do the numbers in your calculator. Okay, and one more example. How many liters of hydrogen are needed to react with 54.3 liters of nitrogen? So we are going to begin with 54.3 liters of nitrogen. We're going to need to convert that to moles of nitrogen, which we will then convert to, let's see, hydrogen's where we're going. We're going from nitrogen to hydrogen. So then we'll convert to moles of hydrogen, and then we will convert to liters of hydrogen. That's our little process here. So 54.3 liters of nitrogen, and we will convert that to moles, and we convert liters to moles using the molar volume. 1 mole of nitrogen would have a molar volume of 22.4 liters of nitrogen. Then we're going to use the mole ratio between nitrogen and hydrogen, which is a 1 to 3 ratio. So 1 mole of nitrogen to 3 moles of hydrogen. And then we're going to convert the hydrogen to the volume liters using the molar volume again. 1 mole of hydrogen to 22.4 liters of hydrogen. And then run this through your calculator. Once you run that through your calculator, you get 162.9 liters of hydrogen. And once again, units, liters of nitrogen cancels liters of nitrogen. Moles of nitrogen cancels moles of nitrogen. Moles of hydrogen cancels moles of hydrogen. And our unit that remains is the liter of hydrogen, which is what we looked for. And so everything in here except for this middle step, I just want to emphasize this. I emphasized this in class. I want to emphasize it again. That's the new step right there, which is this ratio between the elements that we've been given, in this case nitrogen, and we want to know by the question, in this case hydrogen. And it's just the number ratio that's in front, 1 to 3, a 1 to 3 ratio. Just make sure you put the correct one on bottom so that it cancels with the one in the previous step. Other than that, you've done this kind of calculation before. You've done this calculation here before. It's just that new step right there that lets us go across the equation from one chemical to the next. All right.